Bonjour à tous. Okay, so welcome to another video in physical chemistry. Today we'll be talking about reaction kinetics. So reaction kinetics actually talks about how fast a reaction occurs, or so it's the other branch that you look at to determine whether a reaction occurs, because there are two main ideas, right? One is whether it's energetically spontaneous, and another one is whether the reaction is fast enough such that it actually happens, right? So the main governing theory behind kinetics is this thing known as collision theory. Collision theory is based on the idea where the molecules collide with each other and a reaction occurs. And then there are some conditions for this before a reaction is said to occur, right? So collision theory states that reactant molecules must collide with the correct orientation and sufficient energy to produce an effective collision so that there is a reaction. So sufficient energy just means that the energy must be greater than or equals to the activation energy barrier. And the activation energy is just the minimum amount of energy required for a reaction to take place. So if you recall from O levels or something, if you were to draw a energy level diagram, right? So if you were to draw an energy level diagram, it looks something like this, right? Oh, wait, sorry. Okay, something like this. So this is exothermic, right? And then the activation energy is here. So you need to have sufficient, you must collect sufficient energy to be able to reach this stage here on top before you can go to the products, right? These reactants and these products. Okay, so the general format that I use to answer questions regarding collision theory follows this way, right? So you explain the factor first, and then you talk about whether the number of particles increase, whether the particles become closer together. And the main part is that the frequency of collisions increase and the frequency of effective collisions increase, therefore the rate of reaction increases. Right, so this applies for concentration, pressure, surface area to volume ratio. Now the next one is about temperature. So temperature follows this thing known as the Maxwell-Boltzmann distribution, right, which has this general shape over here. This graph was coded in Python, right? So generally at higher temperatures, the curve will broaden, right? So there are two colors here, with the blue one and the pink one. So the pink one is the one at higher temperature. At higher temperature, the curve will broaden and the peak will shift to a value that is of a higher energy, right? The reason behind this is because the area under the curve is always the same, right? The area under the curve is always the same because in the same system, you have the same number of molecules, the same proportion of molecules. So the area under the curve will definitely always be the same. If you increase the temperature, what happens? Temperature is defined as the average. Okay, now temperature is a measure of the average kinetic energy of the system. So if the average kinetic energy increases, it means that on average, the energy of all the molecules increases, right? So if everything increases, it will the energy should all shift towards the right, because now more particles have a greater energy. But to ensure that the area under the curve remains the same, it has to broaden and become shorter, because now let's just say at a temperature over here, right? Okay, if you just look over here at this energy here, this EA, anything that is above this thing now occupies a larger area as opposed to that at the lower temperature. So evidently from this, we can see that as the temperature increases, the average K increases, and now there is a larger proportion of molecules with energy that is greater than or equals to the activation energy. And this results in a higher frequency of effective collision and therefore an increased rate of reaction. Now the Maxwell-Boltzmann curve is also applied in a system known as catalysis, which uses catalysts, right? So catalysts are things that speed up a reaction by offering an alternative pathway with a lower activation energy. But the catalyst itself remains chemically unchanged, which means that it is used up at the start, and then it's regenerated later on. So if we draw a Maxwell-Boltzmann curve for the catalyzed reaction, it will be the same, right? Because there's no temperature change, so the proportion will be the same. But now you have a lower activation energy, so which is shown by EA prime. Yeah, EA prime. So if you were to take the area under the curve at a lower energy, for anything that has energy more than or equals to that of the activation energy, it will definitely be more, right? Because if you can see here, the area under the curve is greater now. So if it's greater, because of this alternative pathway with a lower activation energy, now a greater proportion of molecules have energy greater than or equals to the activation energy barrier, the new activation energy barrier. And therefore, the frequency of effective collisions increases, and the rate of the reaction also increases consequently. So there are a few main types of catalysts. Homogeneous catalysts are catalysts that exist in the same phase as the reactant particles, and heterogeneous catalysts are catalysts that exist in a different phase as reactant particles. So heterogeneous catalyst actually has a sequence of events, which is known as a mechanism or the mode of action of a heterogeneous catalyst. So the first thing is that it has to diffuse to the surface, right? Okay, so this is a catalyst, right? So this is a catalyst. The reactant molecules will diffuse to the surface and absorb onto the surface. So absorption is something like it gets stuck onto the surface, right? So now all of these molecules are now absorbed onto the surface, right? So after absorption, now there is a microenvironment that is favorable for the reactant particles to react with each other. So this lowers the activation energy barrier for the reactant molecules to react with one another on the catalyst surface. And because of this reaction, the product is formed. Upon product formation, they will then, so now we form a product, right? So let's just say you form a product between of them. After this, they will desorb from the surface. Desorption just means getting detached from the surface. And why desorption is important is because if they continue to occupy the surface on the catalyst, right, then there will be no other reactant molecules that can go onto the surface. So it's important that they leave the surface so that the surface is now unoccupied and the active sites are free again for more reactant molecules to adsorb onto the surface. And then the cycle repeats itself. So that's the mode of action of heterogeneous catalysts. This is usually like a 3 to 4 mark question, which is kind of 3 marks, right? So try to remember these few steps. Okay, next is an auto catalyst. Auto means happens on its own, right? Like automatic, right? So why is it called an auto catalyst? Because in the reaction itself, the product is the catalyst to the reaction. So 2 main reactions in your syllabus that you should be familiar with are these 2. And the one bolded is the auto catalyst of the reaction. So what happens is that if you look at the graph, so the blue graph is the concentration graph, it's a concentration time graph. So as the reaction occurs, the concentration remains constant, right? And then it starts to decrease. And as it decreases, it starts to decrease faster and faster and faster, right? Because the auto catalyst is being produced and the reaction speeds up. And then at the end of the day, because there are fewer reactants, it starts to slow down. It slows down around here. And then at the end of the day, it gets used up. So this pink graph here is the magnitude of the rate of the reaction, right? So I use the word magnitude because, well, when it decreases, it's negative, right? So we don't look at negative. We just think of everything as positive, right? So the maximum point is somewhere here in the middle, right? And that's when there's like kind of like a balance. But essentially, the main idea here is that it's an auto catalyst because the product that's produced catalyzes the reaction and then it makes it faster. So that's an auto catalyst. So be familiar with both the graphs and the 2 reactions that are related to it. Okay, the last one is a biological catalyst, also known as an enzyme. So enzymes are present in most biological systems. And this graph here is the rate against the concentration of the substrate. So the substrate is kind of like a reactant, right? So at the start of the reaction, at lower concentrations of substrate, as it increases, it sort of follows something like a first order reaction, which I will cover later on. But essentially, a first order reaction is a reaction in which the rate is proportional to the concentration. Okay, I know this isn't a straight line, but we can sort of describe it as kind of like a first order, okay? So initially it is proportional, and then slowly as you increase it up to a certain point, it is sort of plateaus, and the rate doesn't increase anymore, this regardless of how much the substrate concentration is. And the reason is because just because you have a lot of substrate, no, because you have a lot of substrate, there is not enough enzymes to catalyze the reaction anymore. So the active sites on the enzymes become limiting because there are only that many active sites that can be occupied at any one moment. So there will always be like a batch of substrate reactants that are just lying around, that are not catalyzed at all. So at a certain point, regardless of how much you increase the concentration, the rate is not going to increase. And we call this a pseudo-zero rate reaction. Right, so remember this graph, understand this graph and the shape. So now let's think about kinetics calculation. So there are a few main ways to go about determining what is known as a order of the reaction. Order of reaction just tells you the value in which you raise the power of the particular concentration of a reactant in a rate equation. And this rate equation is experimentally determined, right? So there are a few main experiments that you can conduct. The first one is known as sampling. So sampling just means that you just do one reaction, right? And then you do a titration at different time intervals, and then you measure the concentration at that time, right? So some of the graphs that you will see are something like this, right? So this graph here, these two graphs here show something known as a first order reaction. First order reaction, because the characteristic is that the half-life is constant. So this is a reactant curve, and this is a product curve. So the half-lives are taken at half-lives, right? So half-life is the time at which the concentration is half. So if I start off with, say, like concentration of 10, then I will measure the time taken for it to go to 5, and then I'll measure the time taken for it to go to 2.5, right? And if it's a first order reaction, they should be consistent. If I look at the products is the inverse, right? So when it is 10, it is 0. When it is 5, it is 5. When this is 2.5, this is 7.5, right? So that's how we can go about thinking about it. Now, a clock reaction is one in which you measure the rate of the reaction over time. So there are a few main graphs here which are labeled. So when the order is 0, it's a straight line, because order 0 just means that it is not affected, right? It doesn't take part in the rate equation. So the rate is independent of that particular compound, right? So no matter how much you increase or whatever, the rate of reaction is just going to stay the same. And then this proportional line here is order equals to 1, which is similar to what we saw previously, but the difference is that because it's rate equation, right? And then anything that is a curve is anything that is not 1 and not 0. So it can be any number. It can be half, it can be 2, it can be 3. For the purpose of the syllabus, it's difficult to determine whether it is order 2 unless there are other ways to do it, right? So the rate constant is this value small k here, small k, and it follows this thing known as the however you pronounce it, the Arrhenius equation, right? AE to the power of negative EA over RT. And you can do linear law to convert to this form, and you can then draw a straight line graph out of this, long k against 1 over t, long k versus 1 over t, with the gradient of this graph as negative EA over R, and the intercept is ln A. Okay, the intercept doesn't exist here, but okay, so intercept ln A. So from this, we can actually see that the rate constant is dependent on a few things: the presence of a catalyst, right? Because the catalyst changes the activation energy and it is affected by temperature. So these are two factors that rate is affected by. So another important formula is K times half-life is equals to ln 2. You can derive this formula if you solve the differential equation, but for the purpose of syllabus, it's not required here. Okay. So the last thing that's important is something known as reaction mechanism, which is quite popular. How you do this is, say if you have a multi-step reaction, right? A plus B, and then C plus D forms E. Right. So if the first step is slow, then the rate is just equals to K times A times B. Right. But if the first step is not slow, let me try to make space for this. So if the first step is not slow, then we need to do some adjustments now. Okay, let's just use back the same equation, right? So if now the second step is slow, I still write the rate in terms of the second step, right? Take note now that because C is an intermediate, so we need to write C in terms of A and B. So C, if we do, okay, this is a trick. You do KC for the first step. KC, right? KC equals to C over A times B. You make C the subject, so C equals to K times A times B, right? So you just replace this C here by AB. And then that's your rate equation. So of course, for kinetics, what you need to do is also practice, because this is physical chemistry, right? So this is actually the third and last video in the set of physical chemistry. The order in which you learn these three topics might be different in your school, so watch them in the order that you learn it. But yes, consider getting this set on your own, and if you have any questions, you can consider commenting or signing up for a membership, where we will have live Q&A sessions. So see you in another summary video. Bye bye.